So when we talked about regularization in an earlier video, we gave the sort of a schematic version of the augmented error function. So it's the in-sample error plus some kind of complexity penalty. And so it's usually pretty easy to modify your optimizer so as to include the complexity penalty on top of the in-sample error. Like with gradient descent, you just change the gradient in a little way that will make clear eventually, and things work well. But for linear regression, just like you could actually solve the equation which sets the gradient of the error function equal to the zero vector, for unregularized linear regression, you can also solve for the weight vector in the case of regularized linear regression. So we're just going to do that derivation here. So let me open up the notebook here. So we're going to start with the usual in-sample error for linear regression, which I will denote with a J here. So this is 1 over n times the sum as n goes from 1 to n of wt x minus y, and these are indexed. The n and the y are indexed because they're scalars, and there's a square here. So this is just ordinary least squares error. This is mean squared error, right? And okay, so we want to add in the complexity penalty. So I'm gonna use an alpha here, I guess, but I'm gonna change that to a lambda later in this derivation, and I'll explain why when that happens. So now here we have to write the sum of squares of the weights, but I'm just going to express it like this. So you can check that this is the same thing as the sum of the squares of the weights. I'm using this formula because I know how to take the gradient of that in a slick way, which I will show to you. So let's do this. So the first thing I'm going to do is rephrase this as X is our big data matrix times W minus Y squared. And so hopefully this makes sense to you. You know, we've done this enough times that you know that this is the vector of predictions, right? This is the vector of predictions y hat. So what we're doing here is we're taking the difference between the vector y hat and the vector of true values, and then squaring each entry respectively, and then summing up the result, which is exactly what this expression does, and so they're actually saying the same thing. Okay, and then we have to just kind of keep track of our regularization term as we go along. And I'm just following the derivation that we did a long time ago. So this is the same thing as W transpose X transpose minus Y transpose times XW minus Y. If you don't see why that's true, just try doing it with, you know, just abstract vectors like V and W squared. This is equal to V transpose minus W transpose times V minus W. Oh, I'm moving myself, oops. So just convince yourself that that's true in this simple case, and then you'll believe it here too. So once we have that, now we have to FOIL out this stuff, and when you FOIL it all out, you get WT, XT, XW, minus, well, these are actually going to be the same, like this and that are both just going to be the dot product of Y and Y hat. So I'm going to save myself a little bit of trouble here and write this as 2 times XW Y. Is that right? Sorry, I have to think for a second. No, XT WTY. Okay. and then plus yt y, and then plus the regularization term. Okay, great. So this is the augmented j with w, and now we're going to start taking the gradient. So there's a really powerful formula here that we have. I think we skipped justifying this actually. The argument here is not super hard, but it was not something that we wanted to spend a lot of class time on because a lot of people are kind of soft on their linear algebra. But we at least posted some links to notes that proved this fact. So this is true. And so notice that if A is symmetric, if A is equal to A transpose, then this is just equal to 2AW. So we can use this formula at two places in this derivation. We can use it here because that is of this form, and we can actually use it here too, because we can think of this as being WT times the identity matrix times W. So that makes those gradients easy. The only other gradient we have to do here is this one. Should be a bar over that y there. And what can I say about that? You know what? I messed that part up. Sorry. So this is actually, I got confused because anyway, you know what happened. So this is WT XT times y there. All right, so for the gradient of this part, we're going to think of this as being just some other vector b here. And so we'll think of this as just being WT times b. And there's a formula for that also. So if you're taking the gradient, here W is the variables that we're taking the gradient with respect to, then it's very easy to prove that this is just equal to b. Is that right? B T. All right, so no, just crap. You know what? That's not the formula we need anyway. We need this formula. So we need WT times B, and this is just B. Okay, so now we're ready to apply this formula, these two formulas in these three settings, and we'll take the gradient of J. So the gradient of J is, so we ignore the 1 over n, and then the gradient distributes over sums, just like the derivative does. And in this first place, we apply this formula, and we get 2 times x transpose x times w. And now we apply the formula here, and we get minus 2 xty. And now we don't really need a formula for this because this is just a scalar, and its gradient with respect to w is just the 0 vector because it doesn't have a w in it. Now we apply this formula in this case, which is, we're thinking of it as being like this. So it's 2 times I times w, which is just w. Okay, and we've managed to take the gradient. And now what we have to do is set it equal to 0 and solve. So we set this equal to the 0 vector, and now we're trying to do algebra to solve for the weight vector w. Okay, and I guess I should say that, never mind, I'm not going to say that. So let me multiply in this 1 over n. So this is this becomes, I'm gonna cross out these 2's right now. Everybody see that you could factor a 2 out of everything, so there's no point in writing these 2's. You can divide both sides by 2, and then all those 2's go away. So this is 1 over n times xtx w minus xty. And crap, I missed my 1 over n there. So there's 1 over n here too. 1 over n xty plus alpha w equals the 0 vector. So now we want to collect all the terms that have w and put the other thing on the other side. So this is going to write down a new equality. So this is 1 over n times x transpose xw plus alpha w is equal to 1 over n times xty. I keep forgetting to write the bar over this y. So when we did this earlier in the semester and there was no regularization term, this was not there, and then those 1 over n's canceled out. But now they don't cancel out. But I'm still going to multiply both sides by n, and let's just see what happens. So that gives me xt xw plus n times alpha w is equal to xty. Okay, so now when most people write the formula that you saw earlier, they don't include this n. What they say is this term is just like a rescaling of the weight alpha. So we're still just gonna look for this parameter, whatever it is, and empirically see which one works best. So there's no reason to multiply this n. We'll just give this a different name and call it lambda. Okay. And so let me rewrite the line with that understanding. Whoops. Okay. And I think I lost one leg of my lambda when I hit Control Z too many times. So this is xtx w plus lambda w is equal to xty. Now we can factor out the w, and this is xtx plus lambda times the identity matrix times w is equal to xty. And now this is almost certainly invertible. If x is at all longer than it is wide. And so we can take its inverse and we multiply it times both sides and we get w is equal to xtx plus lambda I inverse times xt times y. And we're done. So this is the formula. It's pretty straightforward to turn it into Python code, but that's going to be your job. Let me see if I can go back here, and I think I showed you the formula, right? It's right there. So what we just did is we just derived this formula, and then an exercise maybe that we'll do in class. You have to actually implement that in NumPy, but at this point it should be pretty straightforward. Oh, and one more thing about the difference between whether you should include the bias weight in the regularization or not. So for the derivation that I just did, we do punish big intercepts. So in other words, we apply regularization to W0. If you don't want to, then where it says I in this formula, you just replace it with the matrix A. And what A is the identity matrix, except that the upper left 1 is replaced with a 0, and then you use the same expression. I tried it both ways on this data set and it didn't make much of a difference, but in some cases it might. If the data naturally has a high intercept. Okay, so that's it, I'll stop. And actually I have to stop recording.